Okay, thank you very much indeed. I'm going to try to outline what I see as the science case for Eve. Good. Well, all of us in the community were delighted that Suki Manabe from GFDL won the Nobel Prize for Physics a couple of years ago, and he did this for his development of the prototype climate models. And indeed, it's the design that we still pretty much use today in IPCC. And this is from a very early paper by Manabe and Weatherald, showing really what is the key reason why we believe climate change is the threat it is, and why we believe it's due to our emissions of fossil carbon. So what the model shows is a warming of the lower atmosphere, of the troposphere, and in particular of the surface. But something that's not mentioned very often is that it also predicts a cooling of the stratosphere. So the upper atmosphere cools. And the physics behind this is not too difficult. And the model also predicted a hotspot over the North Pole. We're looking at averages of temperature around lines of latitude. And of course, all this has come to pass. The Earth is warming, the North Pole is particularly warming, and the stratosphere is cooling. And one of the reasons why we believe this is not, for example, due to the sun becoming warmer is indeed the cooling of the stratosphere. You get a completely different signal if it was due to the warming of the sun. So this has been replicated in countless models around the world in the last 50 years or more. It's the basis of IPCC. So this is what we know, and we know with a great deal of confidence. And I want to just emphasize this point, because I'm going to talk about uncertainties, but none of this is to undermine the fact that we believe very profoundly that we are changing the climate through our emissions of carbon dioxide. The models are based on the laws of physics. They're not just kind of guesswork or empirical rules of thumb. One of the sort of standard laws of physics, which is essentially Newton's second law of motion, is called the Navier-Stokes equations, or equation if you like, vector equation. And it describes the phenomenon of turbulence. And here's a picture of a turbulent fluid. And one of the properties of turbulence is it has what's called self-similarity. So if you were to zoom into a small subsection of that picture, you would see also a sort of chaotic spectrum of eddies from large to small scales. So turbulence, the real world of turbulence, has self-similarity, and this is reflected in what are called scaling symmetries of those Navier-Stokes equations, written as using the language of calculus in terms of partial differential equations. However, we have to solve these equations. They can't be solved by pencil and paper. They're too complicated, so we have to solve them on computers. And once we do that, we actually break these scaling symmetries. So what we do is we split the Earth, the atmosphere, or the oceans up into these grid boxes. And the size of the grid box is pretty much determined by how big your computer is. And within a grid box, we assume that the atmosphere is homogeneous. It's no longer this cascade of turbulent eddies. It's smoothed over. That's the assumption in the computer model. And that allows us to estimate the effect of processes which can't be resolved in the models, so processes that occur within grid boxes or close to the grid box scale, by kind of idealized and simplified formulae. And current IPCC class models have truncation scales around 100 kilometers or so in the horizontal. The problem is that the larger the truncation scale, the more this deliberate and inevitable breaking of the scaling symmetry, the violation, if you like, of the scaling symmetry, will degrade our simulations of climate change. So in particular, there are three important processes. One could name others as well, but I've just chosen to focus on three, which aren't represented by the Navier-Stokes equations, but by these sort of simplified formulae in these homogenized grid boxes. Deep convective clouds, which are so critical, particularly in the tropics, the drag due to gravity waves over mountains, and the mixing of eddies in the oceans. Another thing to say, by the way, is that the Earth's surface is very complicated and very heterogeneous, and that it's, when you look at this is just from Google Maps, taken fairly at random. When you look at that and you see the complexity of the Earth's surface, how sort of approximate our estimates of the transfer of heat and moisture and momentum from the surface to the atmosphere are going to be when we smooth over these topographic irregularities. All right, so what I want to do is to focus on what we don't know as a result of all this. And there are going to be three key points here. The first is how bad the warming is going to be. And I'm sure you've all been involved, or you've watched, or somehow debates where people on the two sides, I mean, it's rare these days to get people who completely deny global warming because the evidence is too strong. But nevertheless, people will say, okay, well, it's here, but it's going to be a problem of no particular importance. It's kind of lukewarm. And then, of course, at the other end of the spectrum, people are concerned about it being an existential threat to humanity. The problem is we don't actually know which of these two is correct. I've grouped together from the 5th and the 6th IPCC assessments estimates of what's called climate sensitivity, how much the global temperature will increase due to a doubling of carbon dioxide. And you can see it's anywhere from 2 to 6 degrees. And 2 degrees isn't an existential catastrophe. It's something that will be, it will create big problems, but it won't be existential. 6 degrees almost certainly would be existential for a large number of people. These uncertainties, probably to first order, the biggest of all the uncertainties is the effect of clouds, how clouds will respond to increasing levels of carbon dioxide. High-level cirrus clouds tend to warm the atmosphere, low-level stratus clouds cool the surface. So how the balance of the two change under climate change is a critical question. And one of the key reasons why it's so difficult to predict how clouds will respond is that clouds themselves are very strongly coupled to the large-scale circulations of the atmosphere. And a thing I'm going to come on and on again to is that our estimates of these large-scale circulations is still very uncertain. I mean, let's take something that's currently in the news now, the El Nino. We're transitioning from 3 years of La Nina, where the Pacific was cooling, Eastern Pacific, to a year now where it seems like the East Pacific is warming into a positive El Nino event. And we know that global temperature and indeed cloud cover is a function of this, probably this single most important mode of interannual variability of the climate system. So a key question then about climate change and the cloud cover, the question of whether cloud cover, how cloud cover will respond to CO2, is the question about how will El Nino or will El Nino or La Nina become more likely or more prevalent under climate change. And the answer is we don't know. The models give different responses, and not only that, the models tend to go in the opposite direction to the observations. So I've just very briefly shown a figure from Pedro Dinizio from NCAR. On the left is the trend in sea temperatures across the Pacific Ocean in observations from the 1980s to the present. And it shows that actually the East Pacific has been cooling, and most of the West Pacific, and certainly into the subtropical West Pacific in both northern and southern hemispheres, has been warming. If you go to the panel on the right there, you'll see kind of what you call a kind of IPCC class model, which has completely the opposite trend. It shows that the East Pacific actually is warming. And that's spawned a number of papers over the years suggesting that the models and the observations are not consistent with each other. There's a discrepancy. And this is a very recent result from Pedro and the NCAR team that going to a high-resolution model, now high by high, we don't actually mean as high as Eve, but in the direction of Eve, is radically changing that picture. So not only will this have implications about, and by the way, it's changing it in the direction towards the observations, which is a good thing. So this seems to be quite a good indication of why resolution is so important. This impacts not only will impact our estimates of global mean temperature and global mean cloud cover, it also has implications for regional climate, which I'll come to. A question which I get asked, I do a number of outreach talks on climate change to local communities in the UK. A question I get asked very, very frequently is there going to come a point where we're kind of wasting our time, a point of no return? And that brings up this topic of tipping points, which is frequently mentioned in the media in particular. Perhaps the archetypal phenomenon which may or may not have a tipping point is the so-called thermohaline circulation. The original simple, somewhat idealized models suggested it does have tipping points. It can be shut off if you freshen, for example, the waters of the North Atlantic sufficiently. The IPCC class models tend not to have tipping points. They just show a slowdown. And frankly, we just don't know, actually, whether this notion of a tipping point is something real or not. It's certainly theoretical. It's a theoretically sound idea, but we don't know. For example, does the topography of Greenland help stabilize there are lots of questions that stabilize the thermohaline circulation. And I'll come back to that in a minute, because that's important. And the third thing I want to stress is regional impacts of climate change. If you are a president or prime minister of a country looking to adapt, a key question is, what's it going to be like for my country? Is it going to be hotter and drier, or predominantly wetter and stormier? And you might go to the IPCC for guidance on that. But if you look at the IPCC figures, you'll see pictures of changes in rainfall, but you'll see a lot of the globe has got this sort of diagonal hatching on it. And if you look down at the table, it basically says no or no robust significant change. So the short answer is we can't get guidance from IPCC about what the manifestation of climate change will be in a typical region of the world, particularly in terms of precipitation. And that's not surprising. If we don't know what ENSO is going to do, how can we say anything about precipitation? Because ENSO take the monsoons. We know typically the Indian summer monsoon tends to be weak during an El Nino event, tends to be strong during a La Nina event. We saw big flooding, I'll come on to this in a second, last year in Pakistan. The La Nina was clearly a dominant driver. The question is, how much was it exacerbated by climate change? But the big question for adaptation in those countries is El Nino going to be more or less prevalent in the future? How will climate change affect the statistics of El Nino? If you can't answer that question, you can forget it. You can't say anything meaningful about adaptation. So we can talk as much as we like about adaptation, but if the science isn't producing that answer, then it's just words. Okay. So I think our inability to know these things has really practical implications. So I want to just briefly outline 4 reasons why Eve is critical, and I'm going to come back to the tipping point business because it has direct and immediate implications about mitigation policy. If we start to cut our emissions after these tipping points, if these tipping points have significant impacts, if we start to cut our emissions, then we're wasting our time. You can't undo. The whole point of a tipping point is you can't undo it. So a key question for mitigation is, are these tipping points imminent? Are we about to pass one? Are we about to pass a point of climate no return? I just briefly mention another issue, because we're clearly, putting a lot of effort into renewables. We need to be sure we're not deploying these in regions where the climate might change adversely for the renewables. And for example, there are questions about the strength of the westerlies in a future climate in, say, Northern Europe. So again, if we're deploying resources in this area, we might make sure that these are future-proofed and that we're not putting them into a region. And of course, the issue of cloudiness for solar panels as well. I've already talked about E for adaptation. You know, if we can't answer basic questions about El Nino, then we can't say anything about adaptation. Loss and damage. I mean, this is obviously a big political issue. People perhaps aren't aware of the fact that the CMIP models typically cannot produce the types of extreme events that we have observed. And often this is rather buried in the reports. And if people are really interested in this, I strongly recommend you don't just read the headlines. So this is from the World Weather Attribution report for the Pakistan flood of last year. The headline makes it seem, oh yeah, extreme monsoon was exacerbated by climate change. But actually, in the report it says, as a conclusion, the models are unable to provide a basis to confidently quantify the change in the monsoon seasonal rainfall intensity with climate change. This is focusing on Pakistan. So if we want to actually quantify how much human-induced climate change affected an extreme event like the Pakistan flood, we can't do it with CMIP models. We've got to move to something like EVE. And just finally, Thomas, I know I'm short of time. I do want to mention geoengineering. The EU actually, I took this from the Financial Times last week. It's something a lot of us don't like talking about, but for example, the Commission is now, asking for an international effort to really try to quantify the impacts of geoengineering. Do we really want to take the chance if we don't know whether we'll be shutting down the monsoons or reducing moisture supply to the rainforests? These are the kind of questions we need to know, which CMIP models can't answer. Okay, so what's EVE? EVE is about trying to represent these processes by the laws of physics. We think that can be achieved with 1 kilometer models. We'll certainly need dedicated exascale computing. We'll certainly need machine learning in various guises. I'm not going to completely skip over machine learning. I could give an hour talk on it, but I think the next speaker will say it much better than me. There are other numerical techniques like stochastic rounding, which I think are going to be important. But above all, it needs a focused approach, pooling international effort from scientists across the world. I think a natural timescale is up to, say, around 30 to 50 years, maybe, that sort of ballpark. Certainly not hundreds of years. We'll still need CMIP to do longer timescales, but I think this is a natural focus for the multi-decadal timescale, which I think was mentioned. Some of us have been bleating on about this for a long time now. My colleague Jay Shukla in the audience led a paper in BAMS, and I wrote this thing in Physics World in 2011. But I just want to say more recently, Paul Nurse, who is a Nobel laureate, he was president of the Royal Society in the UK, and he currently is director of the Crick Institute for Molecular Biology. He did a report for the UK government on research, the research landscape. And I just want to read from a couple of sentences. He's a very influential person, by the way, much more than I am. There are research areas of global strategic importance where new multinational funded institutes or international research infrastructures could be contemplated. An obvious example being an Institute of Climate Change built on the EMBL model. EMBL is the European Molecular Biology Laboratory, which incidentally isn't one physical institute, it's actually a network of institutes around Europe. And that's very much as Bjorn said, that's very much the picture we have, but now institutes around the world. Such institutes are powerful tools for multinational collaboration and bring great benefits, not only internationally, but for the host nation. Okay, so I have finished. I hope you understand, just to reassert, I am 100% believing that what we are doing to the atmosphere, we are changing the climate, there is no doubt about that, but we don't have the tools to assess that as accurately and as precisely as we could do. We're kind of looking at the world through blurred, distorted glasses, and we could do so much better. Eve isn't about incremental science. It's not about bringing another epsilon to CMIP6. It's about utterly transforming our capabilities. And I think it's obvious, I hope it's obvious, how the science will feed into all of the impacts and applications that people have talked about. And we have to do this in partnerships with institutes around the world. This is a global problem. We're all in it together.